Hello students, welcome to the physics lesson. Today, we will discuss your mid-exam. Since we cannot do it in the classroom, I will give you the discussion in the form of videos. Now, let's begin from number 1. A spring is hung from a beam and a load is suspended from it. Figure 1.1 shows the spring before and after suspending the load. 1a, using the letters on figure 1.1, state which distance you would need to measure in order to find the extension of the spring. Extension means the difference in length. In the figure, we can see that the initial length of the spring is y. After the load is added, the length of the spring becomes z. So, the extension of the spring is the distance between y, z, or zy. That's the answer for question 1a. Distance yz or zy. Question 1b. An experimenter measures the extension of the spring with different loads and obtains the graph shown in figure 1.2. Question 1bi. When the experimenter hangs an unknown load on the spring, the extension of the spring is 1.7 cm. Use figure 1.2 to find the weight of the unknown load. Show clearly on the graph how you obtain the value. Let's look at figure 1.2. To find the unknown load, first we have to locate the position of 1.7 cm extension on the graph. Now let's count from 1. 1, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, and then 1.7. So this is the location of the 1.7 centimeter. Now, draw a horizontal line from the position of 1.7 centimeter extension until the line touches the line of the graph. We will get this line. After that, draw a vertical line from the point where the line of the graph and our horizontal line meets, downwards until it touches the x-axis. This is the line. The point where the vertical line meets the x-axis is the value of the load. Let's count from 4, 4.1, 4.2. So 4.2 is the point where the vertical line meets the x-axis. This means that 4.2 is the value of the load. Now we can answer question 1bi. Question 1bi, weight equals to 4.2 Newton. Question 1bi. State the value of the tension in the spring when this load is hanging from it. After the load is hung on the spring does not move. Please recall your memory about Newton's first law of motion. If a body does not move, then the resultant force on the body equals to 0. If the resultant force on the spring equals to 0, then the value of the tension equals to the value of the load. Once again, if the resultant force on the spring equals to 0, then the value of the tension equals to the value of the load. Why? Because the direction of the tension is upwards, while the direction of the load is downwards. This means that tension and load have opposite direction. Therefore, they will have the same value, so that the resultant can be equal to 0. Remember, the resultant of two opposite forces is the subtraction of their magnitudes or values. So, to answer this question, tension equals to the weight or the load, which is 4.2 Newton. Question 1b triple I. The load is pulled down further. State what happens to the tension in the spring. When the load is pulled down, the tension increases because it has to follow the rule that the resultant force equals to 0 when the body does not move. So that's the answer for question 1b triple I. The tension increases. Question 1b IV. After being pulled down, the load is released. State what happens to the load immediately after it is released. After the load is released, the downwards force will immediately decrease. Then the tension will be greater than the load. Remember, the direction of the tension is upwards. So, the tension will pull the load upwards. The answer can be the load is pulled up by the tension of the spring, or the load goes up, or the load moves upwards. We will continue with number 2. The extension load graph for a spring is shown. The unloaded length of the spring is 15 cm. When an object of unknown weight is hung on the spring, the length of the spring is 16.2 cm. Use the graph to calculate the weight of the object. Show clearly on the graph how you obtain the result. The figure shows an extension load graph. That means, to find the load or the weight, we have to know the extension of the spring. Extension is the difference between the loaded length and the unloaded length. The loaded length of the spring is 16.2 cm, while the unloaded length of the spring is 15 cm. Then, the extension of the spring is 16.2 cm subtracted by 15 cm, or 1.2 cm. Find the point where the value of the extension is 1.2 cm. Let's count from 1. This is 1, 1.1, 1.2. Draw a horizontal line from 1.2 cm extension until the line meets the line of the graph, like this. Then, draw a vertical line from the point where the horizontal line and the graph lines meet until it reaches the x-axis. This is the vertical line. Read the value of the point where the vertical line meets the x-axis. This point is the value of the weight. We can see that the value of the weight is 3 Newton. So that's the answer to this question, 3 Newton. Question number 3. An IGCSE student is investigating the relationship between the extension of a spring of unstretched length and the load hung on the spring. The apparatus is shown in figure 3.1 below. The spring is shown larger than its actual size. 3a. The data collected by the student are presented in figure 3.2. 3ai. Consider the readings that the students should take and write appropriate column headings with units in figure 3.2. To investigate the relationship between the extension of a spring and the load hung on the spring, there are only 2 readings need to be taken by the student. The readings are load or weight in Newton and length in millimeter. Why in millimeter? It is because the third column, this one, the extension, already used the unit of millimeter. Then the length must also be in millimeter. Question 3a double I. Complete the third column in the table by calculating the extension of the spring. To fill in the extension column, we have to subtract each length with the initial length. The initial length is the length of the spring when the load is equal to 0. Therefore, the initial length of the spring is 25 mm. Now let's fill in the extension of the spring one by one. The first row, this is 0. Why? Because 25 minus 25 is 0. Second row is 30 minus 25, which is 5 mm. The third row, 35.5 minus 25. We will get 10.5 mm. The fourth row is 40.5 minus 25, which is 15.5 mm. The last one is 46 minus 25, which equal to 21 mm. Question 3a triple I. State the unstretched length of the spring. The unstretched length equals to the initial length. The initial length here is the 25 mm. Therefore, the unstretched length is also 25 mm. Question 3a IV. On figure 3.3, plot the load and extension data from the table. Draw a line of best fit for the graph. Let's check which data we have to plot on the graph. This is the load and this is the extension. So we will use column 1 and column 3 for the data of our graph. First, we have to label the x and the y axis. You can choose which one to be the x-axis and which one to be the y-axis. In this drawing, I will show you how to do both. In the first drawing, the x-axis is the load, while the y-axis is the extension. Don't forget to put unit on the label. The extension unit is millimeter, the load unit is Newton. Then, write down the values of the scale. You have to choose the scale for your graph carefully. Make sure your graph can fit in the space provided. Also, your graph must not be too small. At least 3/4 of the space provided must be covered by the line of your graph. This skill will be developed along with your study in DCP program. This is the 0, and then 5.0, 10.0, 15, 20, and 25. So you can see on the y-axis, I choose the scale division of 5 mm for each 10 small blocks. For the x-axis, 0.1, 0.2, 0.3, 0.4. So every 0.1 Newton, there will be 10 small blocks. After the values filled in, plot the data on the graph paper. The data are 0 with 0, 0.1 with 5.0, 0.2 with 10.5, 0.3 with 15.5, and 0.4 with 21. After all the data plotted correctly, draw a line of best fit for the graph. Drawing a line of best fit is also a skill that will be developed along your study in DCP program. But now, the meaning of drawing the line of best fit for you is trying to draw a line which passes through as many crosses as possible. Like this one. Our first type of graph is done. Before we move on to the second type of graph, I will show you how to calculate the spring constant for this graph. So, we will answer question number 3AV before drawing the second graph. This is done to avoid the mixed up of working, because the working for question number 3AV depends on the choosing of the axis. The working is different for the first and the second type of graph. The spring constant equals to load over extension. So, for the first graph, the spring constant equals to run over rise, because the load is on the x-axis and the extension is on the y-axis. Once again, spring constant equals to load over extension. So for this type of graph, the spring constant equals to run over rise. Draw a right angle triangle on the graph to mark which 2 points are used to calculate the spring constant. I choose 0.3, 15.5, and 0, 0. So, my right angle triangle looks like this. The run over rise equal to 0.3 over 15.5. So, the spring constant equals to 0.3 over 15.5 or 0.019 Newton per millimeter or 0.19 Newton per centimeter. That's the value of K. Now, let's draw the second type of graph. In the second drawing, the x-axis is the extension in millimeter, while y-axis is the load in Newton. Once again, don't forget to put unit on the label. Then write down the values of the scale. I want to remind you that you have to choose the scale for your graph carefully. Don't make it too small, but also it has to fit in the space provided. At least 3/4 of the space provided must be covered by the line of your graph. I choose the same scale as before. For the extension, I divide it into every 5 mm. As for the load, I divide it into 0.1 Newton. After the values filled in, plot the data on the graph paper. 0 with 0, 5.0 with 0.1, 10.5 with 0.2, 15.5 with 0.3, 21 with 0.4. After all the data plotted correctly, draw a line of best fit for the graph. Try to draw a line which passes through as many crosses as possible, like this one. Our second type of graph is done. Let's calculate the spring constant for this graph. In the first graph, the spring constant equals to load over extension or run over rise. In the second graph, the spring constant still equals to load over extension. But because now the load is on the y-axis while the extension is on the x-axis, then the spring constant now equals to rise over run. Once again, spring constant equals to load over extension. The load now is on the y-axis. The extension is on the x-axis. So, the spring constant now equals to rise over run. So, be careful. Draw a right angle triangle on the graph to mark which 2 points are used to calculate the spring constant. I choose the same points, 15.5 with 0.3, this one, and 0 with 0. So, my right angle will look like this. The rise over run equals to 0.3 over 15.5. Then the spring constant equals to 0.3 over 15.5 or 0.019 Newton per millimeter or 0.19 Newton per centimeter. That's the value of our spring constant or K. The results of the two different working are the same and must be the same. Then our calculation is correct. In the test, you only need to draw one type of the graph. So, choose which one you prefer to draw. Question 3b. The student decides to repeat the experiment using a spring made of a different metal in order to study how the extension may be affected by the metal from which the spring is made. To make a fair comparison, other variables must be kept constant. Suggest 3 variables that the student should keep constant. The first one is the initial length of the spring. Second variable, the amount of load added each time to the spring. The third one, the diameter of the wire used to make the spring. Those are the three variables that the student should keep constant. We continue with question number 4a. A spring of original length 3.0 cm is extended to a total length of 5.0 cm by a force of 8.0 Newton. Assuming the limit of proportionality of the spring has not been reached, calculate the force needed to extend it to a total length of 6.0 cm. When the limit of proportionality of the spring has not been reached, the force is proportional to the extension of the spring. So, as the first step, we have to calculate the extension of the spring for the first condition. The initial length or the original length of the spring is 3 cm. It is extended to a total length of 5 cm. So, the extension is 5 cm minus 3 cm, which equal to 2 cm. This extension is produced by 8 Newton force. So be careful, the 5 cm here is not the extension of the spring. It is the final length of the spring when it is pulled by 8 Newton force. Then we can conclude that for 1 cm extension, 4 Newton force is required. How to get this? We get it from here. 2 cm is produced by 8 Newton force. Once again, 2 cm extension is produced by 8 Newton force. So it means 1 cm extension will be produced by 4 Newton force. The second extension, the spring is now pulled from 3 cm until it reached a total length of 6 cm. So, our second extension is 6 cm minus 3 cm or 3 cm. This is our second extension. Once again, be careful. The 6 cm here is the total length, not the extension itself. Okay? So you have to subtract the 6 cm here by 3 cm to get the correct extension. Then the force required is 3 times 4. 3 is the 3 cm here multiplied by 4. 4 comes from here because for 1 cm extension, 4 Newton force is required. So, for 3 cm extension, the force required is 3 times 4, which is equal to 12 Newton. That's the answer for number 4a. The force equals to 12 Newton. Question 4b. Figure 4.1 shows the arrangement for an experiment on moments. The spring exerts a force F on the meter rule. BI. On figure 4.1, mark another quantity which must be measured to find the moment of the force F. Moment of a force equals to force times perpendicular distance from the force to the pivot. So, another quantity which must be measured to find the moment of the force F is the perpendicular distance from force F to the pivot. The distance is this one. You have to mark with arrows on both sides of the line to show which the distance start and end. And also write down the label here. BII. State how the moment of the force F is calculated. Just like I have said before, moment of a force equals to force times perpendicular distance. So, the moment equals to force F here times distance. We already labeled the distance, so you don't have to put perpendicular distance on the equation. It's just distance. Question number 5. Figure 5.1 shows part of the extension load graph for a spring. The spring obeys Hooke's law between points A and B. 5AI. On figure 5.1, complete the graph between A and B. When the spring obeys Hooke's law, then the graph will be a straight line. So, just draw a straight line between A and B, like this one. 5AII. State the name of point B. The name of point B is limit of proportionality. Question 5B. The spring has an unstretched length of 4 cm. An object is hung on the spring, and the spring length increases from 4 cm to 6 cm. Calculate the mass of the object. To answer this question, we have to go back to the graph. From the graph, we know that 12 Newton force produces 3 cm extension. Once again, 12 Newton force or load produces 3 cm extension. This means that 1 cm extension is produced by 4 Newton load. Just divide the 12 Newton with 3 cm. So, we get 1 cm extension is produced by 4 Newton load. The extension in this problem is 6 cm subtracted by 4 cm. So be careful guys, our initial length is the 4 cm. The final length is 6 cm. So the extension equals to 6 minus 4, which equals to 2 cm. If 1 cm extension is produced by 4 Newton load, then 2 cm extension is produced by 4 times 2 or 8 Newton. So, the load to produce 2 cm extension is 8 Newton. Now, let's calculate the mass. Mass equals to load divided by 10. The 10 here is the gravity. So, 8 divided by 10, which is equal to 0.8 kilogram. This is the mass of the load which produce 2 cm extension to make the spring has a final length of 6 centimeter. This is our answer, 0.8 kilogram. Question number 6. Figure 6.1 shows a thin sheet of metal suspended from a hole in one corner at A. The weight of the metal is 0.1 Newton and the center of mass is at B. 6a. Describe in detail how you would experimentally determine the position of the center of mass of the sheet of metal. Prepare a pin, a piece of thread, and a plumb line. You can replace the plumb line by a weight or a load, just a small one. Or you can also use a small stone. Mark 2 other points on the metal sheet, each one on each corner of the metal sheet. Suspend the card freely with a pin at A. Hang the plumb line with a thread on the pin. Mark the vertical line made by the thread. Repeat the same procedure for the other 2 points. The center of mass is the point where the 3 lines intersect. This is the complete description for experimentally design of determining the position of the center of mass. Question 6b. The sheet turns because of the moment of the weight about point A. Define what is meant by the moment of a force. Moment of a force is force times perpendicular distance from the force to a pivot, or the turning effect of a force about a pivot. Number 6c, Figure 6.2 and Figure 6.3 show a thick piece of wood with one corner on a table. Figure 6.4 shows the same piece of wood balanced on the table. B is the center of mass. Ci. Explain why in Figure 6.2 the piece of wood falls to the right and in Figure 6.3 it falls to the left. Because the weight in Figure 6.2 causes a clockwise moment or falls on the right side of the pivot, while the weight in Figure 6.3 causes an anti-clockwise moment or falls on the left side of the pivot. Cii. Suggest how the thickness of the wood in Figure 6.4 affects its stability. The thicker the wood, the greater its stability because it will have larger base area. Question number 7. A pivoted uniform bar is under the action of the forces shown. The weight of the bar is 10 Newton. Draw the position of the weight on the figure. The position of the weight is at the center of mass of the uniform bar. For a uniform bar, its center of mass is right on the middle. So, this is the position of the weight. Remember, you have to draw this line starting from the middle of the uniform bar. Goes vertically downwards. And then put label on the arrow. Guys, you are not allowed to draw this line and the arrow on the top of the uniform bar because it is said that the weight is on the center of mass of the uniform bar. So you have to draw it started from the center or the middle part of the uniform bar. Number 7b, the distance of the weight from the pivot. The position of the weight is right on the middle of the uniform bar. This means that the distance of the weight from both ends of the bar is 5 meters. The distance of the pivot from the left end is 6 meters. This one. So, the distance of the weight from the pivot is 1 meter, because 5 plus 1 equal to 6 meter. So that's the answer for number 7b, 1 meter. Number 7c, calculate the total clockwise moment. We have to go back to the figure to see which forces produce clockwise moment. The 15 Newton force and the 10 Newton force both will produce clockwise moment. Why? Because they both are on the right side of the pivot. Please remember, when a force is placed on the right side of the pivot, it will produce clockwise moment. The distance of the 15 Newton force from the pivot is 2 meters. The distance of the 10 Newton force from the pivot is 4 meters, not 2, yeah? Because 2 meters is only until here. You have to measure the distance from the position of the force until the position of the pivot. So the distance for the 10 Newton force is 4 meters, not 2 meters. So the answer for number 7c is 15 times 2 plus 10 times 4 equal to 30 plus 40. This equal to 70 Newton meter. Number 7d. Calculate the total anti-clockwise moment. Once again, we have to go back to the figure to know which forces produce the anti-clockwise moment. On the figure, we can see that weight and the 20 Newton force here both are on the left side of the pivot. When a force is placed on the left side of the pivot, it will produce anti-clockwise moment. So these two forces, the weight and the 20 Newton force, both will produce anti-clockwise moment. The weight of the uniform bar is known in the problem as 10 Newton, this one. The distance of the weight from the pivot is 1 meter, and the distance of the 20 Newton force from the pivot is 6 meters. So the answer for number 7d is 20 times 6 plus 10 times 1 equal to 120 plus 10 equal to 130 Newton meter. Question number 8. Figure 8.1 shows a circular metal disc of mass 200 gram freely pivoted at its center. Masses of 100 gram, 200 gram, 300 gram, 400 gram, 500 gram, and 600 gram are available, but only one of each value. These may be hung with string from any of the holes. There are 3 small holes on each side of the center. One at 4.0 cm from the pivot, this hole and also this one. One at 8 cm from the pivot, this hole and also this one. And one at 12.0 cm from the pivot, this one and this one. The apparatus is to be used to show that there is no net moment of force acting on a body when it is in equilibrium. Question 8a. On figure 8.1, draw in 2 different value masses hanging from appropriate holes. The values of the masses should be chosen so that there is no net moment. Alongside the masses chosen, write down their values. There are some possible correct answers for this question, so your answer can vary. The important key to answer this question is make sure that the mass times distance for the left side of the pivot equal to the mass times distance for the right side of the pivot. As an example, I choose 300 gram and 200 gram masses. The problem now is where to put these masses. After you determine which masses you want to use, find the LCM or the lowest common multiplication of your masses. My masses are 300 gram and 200 gram. So, the lowest common multiplication for my masses is 600. That means we have to put the 300 gram on the second hole and the 200 gram on the third hole. You can exchange the position of the 300 gram and the 200 gram. So the 300 gram can be on the right side and the 200 gram can be on the left side. But still, you have to put the 300 gram on the second hole of the right side. And the 200 gram must be put on the third hole of the left side. And also, you have to remember, you are only allowed to put one mass on each side of this center. If you put both masses on the left side or both masses on the right side, you will not reach equilibrium condition. Why the 300 gram must be put on the second hole? And why the 200 gram must be put on the third hole? The answer is because 300 times 2, there are 2 holes from the position of the 300 gram until the pivot equal to 600. And 200 times 3, there are 3 holes from the position of the 200 gram until the pivot is also equal to 600. Question number 8b. Calculate the moments about the pivot due to the 2 masses chosen. The answer to this question is based on your choice in 8a. So, I will answer this based on my choice in 8a. First, convert the masses into kilogram. To convert the masses into kilogram, divide each of them by 1000. Then, the 300 gram will become 0.3 kilogram and the 200 gram will become 0.2 kilogram. Because moment is force times distance, we must convert the mass into weight. Just multiply each mass by 10 to get the weight of each mass. So the 0.3 kilogram becomes 3 Newton, while 0.2 kilogram becomes 2 Newton. Next, multiply each weight by the distance about the pivot. We have to go back to the figure to see what are the distances for each weight. We can see here that the 300 gram is 2 holes away from the pivot. So, the distance of the 300 gram from the pivot is 8 centimeter. The 200 gram mass is 3 holes away from the pivot. So the distance of the 200 gram is 12 centimeter from the pivot. You can see the distances of each hole on the problem here. The SI unit of moment is Newton meter. Therefore, I will convert each distance from centimeter into meter. The distance of the 300 gram mass from the pivot is 8 centimeter, which will become 0.08 meter, while the distance of the 200 gram mass from the pivot is 12 centimeter, which will become 0.12 meter. Remember, just divide the number in centimeter by 100 to convert it into meter. So, the moment due to the first mass is 3 times 0.08, which equal to 0.24 Newton meter. While the moment due to the second mass is 2 times 0.12, which equal to 0.24 Newton meter. Both moments must be equal. Otherwise, your answer in 8A is wrong. Now, let's fill in the answer to the provided space. Moment due to first mass is 0.24 Newton meter. Moment due to second mass is also 0.24 Newton meter. Number 8C. Calculate the force on the pivot when the two masses chosen are hanging from the disc. The force on the pivot equals to the sum of the weights. The weights are 3 Newton and 2 Newton. Then the force equals to 3 plus 2 or 5 Newton. This is the end of the mid-exam discussion. If you have any question regarding to the discussion, you can ask me directly in the next week. Next week, we will have Zoom meeting, so you can ask anything about this during the meeting. See you next week. Bye guys.